This is my talk on Chronomaly. So Chronomaly is an exploit that I wrote for CVE 2025-38352, and I'll get into this, right? So a little bit of a quick what I'll cover. So I'll break down the CVE. I'll break down what the vulnerability is about. I'll explain how to trigger the vulnerability, and then I'll explain how in the Linux kernel you can use a linked list, a simple linked list. If you can corrupt it in a specific way, you can actually cause a use after free whenever you want. It's a very controlled use after free. And I'm going to explain how you can use that to, in this case, for this specific vulnerability, you can get an arbitrary decrement primitive. You can just decrement some value in whatever kernel memory space that you want, and then you can use that at the end to get full LPE, right? So that is, yeah, that's that. I'll just talk a little bit about me, not too much. For my day job, I am a lead security researcher at Zelic. It's a blockchain security company. Obviously, this has nothing to do with the blockchain, but that's just my day job. In my free time, I do low-level vulnerability research. So recently, within like the last 6 or 7 months, I've been focusing on the Linux kernel. But before that, I was doing V8 stuff. Back then, I used to work at Dataflow Security, so I did Chrome and V8 and Android. And recently, I have won the Zero-Day Cloud Competition's Linux kernel category in December in 2025, so 6 months ago. So, so there's a few assumptions about the audience here. I can't explain everything about this vulnerability within this 1 hour time slot. It'll take too much time. So I'm just going to assume that you guys are somewhat familiar with kernels at a very basic level, nothing too fancy. I'm going to assume that you guys are familiar with signals in Linux. So SIG-SEG-V or SIG-Abort, whatever, any signals, how they get sent between processes and threads. And also, yeah, you have a basic understanding of processes and threads and how they work in Linux. OK, so quick disclaimer as well. Sorry, I'm going to get to the talk. I've had to simplify a lot of my explanations down, right? So if you ever hear me say something and you're like, oh, that technically that doesn't make sense, that's not correct, well, that's why, right? I have to simplify a bunch of stuff down to make sure that I can cover everything within this time. If you have any questions, please feel free to ask me afterwards, or I do have a 3-part blog post series on this vulnerability and the exploit, so you can have a read of that as well. So yeah, OK, let's get started, right? So why did I choose, I have this thing on my screen, sorry. OK, yeah. Why did I choose this project? Why did I even get into this, right? Because for any research project, you need some sort of motivation, right? For me, the motivation was mainly I wanted to find a vulnerability that others have tried to exploit and haven't succeeded, or something that doesn't have a lot of information about this exploit. So on this screenshot that you can see, it's basically from the one blog post that existed at the time when I first started. There was only one blog post that talked about this bug, and it essentially just described the bug. They made a proof of concept, but they didn't explain how to do it because they didn't want other actors to be able to use it for malicious purposes, right? So that was the only thing that was available at the time when I first started. And based on some Twitter comments, I saw that there were other researchers who had tried to exploit the bug, but they were having a very difficult time. Or if they were successful, they didn't share the information, right? So my goal in this case was exploit this bug. Hopefully, it's a complicated bug. I can learn a bunch of things, and I can share it with people. So what is this bug? This bug was a race condition in the Linux kernel's POSIX CPU timers implementation, and it leads to a use after free. And based on an Android security bulletin, this bug was exploited in the wild in a limited context because this only affects a very certain amount of kernel configurations, which relate to the kernel versions, right? The bug affects a bunch of kernel versions, but only certain versions have a config that enables exploitation. OK, so that's that. Let's now dive into the vulnerability. Now, when talking about this vulnerability, I have to cover a bunch of prerequisite stuff, so I'm going to go through these as quickly as possible to get to the actual bug. So first things first, CPU scheduler and timers, right? So in the kernel, you have a scheduler, I guess, component, right? It determines how processes and threads share CPUs. So if one process is executing, when can it pause and allow another? Let's say you're running Chrome, right? When can you pause Chrome and allow, I don't know, VLC media player to play your movie or something, right? So that's what the scheduler does. And the scheduler has multiple different clocks, and the clocks determine how often a tick happens, right? And on every single tick, the CPU causes an interrupt. So whatever code is running, it doesn't matter if it's in the kernel or if it's in userland, whatever code is running, as long as it's not holding some critical mutex or semaphore or whatever, the code can get paused, and it'll jump over into this interrupt context where it does a bunch of things, but the important thing in this case for this vulnerability is this run. Can you guys see the? You can't see the. Oh, wait, hold up. Let me see. Yeah, you can see the cursor. Yeah, OK. So it runs this function, this run POSIX CPU timers function. And this function, all it does is it checks, are there any CPU timers that were armed before, and now they're expiring, they're ready to be fired. If there is, let's handle them. That's all it does, right? Now, what is a CPU timer? A CPU timer is just a way for a user-land program. It can create a timer, and it can say, hey, in 2 milliseconds, or some absolute time like today at 5 p.m., I want you to send a signal to this process, or run this bit of code. That's just it, right? That's a CPU timer. And one important thing to note here is that CPU timers cannot be deleted if they are armed. You have to wait for them to be disarmed, or they have to be fired first before you can delete them. Otherwise, you get use after freeze, right? You can delete a timer, and then gets processed afterwards, get use after free. OK, so this function, hopefully that's readable. So this function sort of just, it's not important, the code here, but essentially all it's doing is there's a fast path check down here, and it's just checking, are there any expired timers? If there aren't, just return. So 99% of the time, this function that runs in the interrupt context is very quick. That's why you don't see your computer lagging or whatever when you're doing normal stuff. But when you have a timer that has expired, then it needs to go and call this internal run POSIX CPU timers function, and that's the expensive thing that happens. OK. So now the other thing we have to talk about is how tasks, in this case, so a task can be a process or a thread, to talk about how they exit and how they become a zombie task. And the reason is that a zombie task is very important to understand for this vulnerability, right? So whenever a task exits, it calls this doExit function in the kernel. And typically, for most tasks, the task immediately gets set to a dead state. Now, in a dead state, all the task can't really do anything. It's just dead, right? All the things get freed. It's just dead. Whatever. That's fine. Now, in certain situations, the task can become a zombie task. And zombie tasks must either be reaped by a parent task to turn it dead, or a ptracer task, such as, let's say you have GDB or something. You're debugging the task. So the GDB in this case would be the ptracer process, right? And yeah, you would have to reap it. That's just a technical term. It just means you wait on it to exit, and then it becomes dead. So now, knowing how to create a zombie task is very important. So I'm just going to quickly just explain that. So if you want to create a zombie task A, you would create task A, and then you would, in this case, for this vulnerability, you create task B, and you ptrace task A with it. So, and when this happens, if you this doExit function that I mentioned here, it will actually call this function exit notify. And the logic in this function is simple. It first always transitions the task to a zombie, and then it checks, is it being ptraced? If it is, just leave it as a zombie. Don't touch it anymore. Otherwise, just reap it and update it to dead. OK. So why is a zombie task important in this context? So the main reason is that zombie tasks still have their signal handling structure intact, whereas dead tasks, it's removed for dead tasks. And I'll show some code that shows that in a future slide real quick. But the reason it's important is because a zombie task can still consume CPU time, right? So if you look at this diagram on the right, the doExit function, basically it just does a bunch of things. And then it calls exit notify, which is this function that turns a task into either a zombie or a dead task. And then it does a whole bunch of other things. And then it finally calls this function called doTaskDead. At this point, even if the task is a zombie, it's basically dead because it cannot consume any more CPU time. And the reason consuming CPU time is important is because the interrupt that happens on each tick of the CPU that we just talked about before, that requires CPU time to be consumed. So after a certain amount of CPU time is consumed on each tick, it'll cause an interrupt. So basically, after this doTaskDead function is called, the task cannot cause any more interrupts. So at that point, it's just dead. So we basically have this short time window where the task is a zombie, after exit notify is called, and before doTaskDead is called, where you can cause a CPU interrupt. And so yeah, you can, on the diagram on the left here, you can see you can technically cause a CPU interrupt on a zombie task after exit notify has been called. So yeah, so the idea here, I guess, for the bug on how this bug was found by the original whoever found it, or yeah, how you can find a similar bug, I guess, is you would ask yourself when you see this code, what happens in this short time window, what happens if an interrupt occurs for a zombie task, right? Because a zombie task, it's only a zombie for a short period of time until it's just dead. So that's the question, and I'm just going to take a quick detour, and this is how I think I would find this vulnerability myself, right? I would study up on the CPU scheduler, I would study up on tasks, and at some point, after learning all of this, I would ask myself this question. Since the scheduler interrupt can occur literally at any time, right? Even if the kernel code, even in do exit, a task is exiting, it can pause at any point inside this function and go into the interrupt context and run some other function. So what are some weird scenarios where a kernel developer might have forgotten about, right? An interrupt can happen here, but they didn't think about it or whatever, right? So that's how you would find this vulnerability. Now, to understand how to trigger this vulnerability, we have to combine these two things, right? CPU scheduler and timers concepts and task exiting, right? So that's this slide here. So when a zombie task gets reaped by a ptracer or a parent task, the task signal handling structure, which is this task sighand structure here that's highlighted, it gets set to null. And this structure is important in this context because CPU timers use this structure extensively for various things. And I'll show that in a few future slides, sorry. And this exit signal function is what gets called when a task is reaped. So, and just real quick, this is how you would reap a task. So let's say you have some task that's p-tracing some other task. You would just call wait PID on it, and with the thread ID or the process ID of the task that you want to reap. And this is a blocking system call. So if the task is a zombie, it just returns instantly and just reaps it, and it's dead. Otherwise, it'll block and wait until the task becomes a zombie. So now, once a timer is armed, as I mentioned before, you cannot delete it or free it until it either fires or it gets expired, right? And that's readable. OK, cool. So that logic is in this function called POSIX CPU timer delete. And in this function, you can see the first thing it does is it tries to lock or acquire a lock on this signal handling structure. If it fails to acquire this lock, meaning, let's say the task was reaped or it just died, so did I show that code already? Yeah, I did. Yeah, so you can see it gets set to null here when the task is reaped. If that happens and this is null, it fires some warnings which don't do anything in the Linux kernel. It's just some warnings in the kernel logs, and then it actually allows the timer to be deleted, which makes sense. If the signal handling structure doesn't exist, the task is dead anyway, so the timer can be freed. It just makes sense. And this lock task sighand function, its flow sort of looks like this, right? It just checks, does this signal handling structure still exist? If it does, then you acquire the lock, this sig lock, and then you return the structure. Otherwise, just return null. So that's why this structure is important for this bug, for CPU timers. This is how the check happens. Like, is the timer armed? It needs this structure to check for this. So the other side of things is in that interrupt context. So remember that run POSIX CPU timers function. That actually calls into this handle POSIX CPU timers function. And this function does the same similar thing with the signal handling structure. It first tries to acquire this lock. If it fails, meaning the task died or whatever, right, it's just gone, then the timers don't need to be handled, right? If the task is dead, it doesn't matter what signals it sends, so just return. But if it succeeds, then it goes in and checks all potential timers that this task might have created. And if any of them are expired now and ready to be fired, it'll accumulate it into a local linked list, a local variable, and then it'll release this lock, and then it'll process the timers, right? And it's important for it to do this because if it doesn't do this, like lock the sighand structure and then check the timers, what can happen is another process, another thread, can reap this task as a zombie, or it can just die, and then it can free the timers before this processing happens at the end here, right? So that's why it's important that it does it like this. But if you look closely enough, you'll realize that there is a race window here, right? Because the siglock structure is, the siglock mutex is released before the timers are processed, right? So now you have this question of, can we, I guess, reap this task and delete the timers in this short window, right? You let the sighand lock get acquired. In this case, it has to be a zombie task, right? Because a zombie task is the only thing that can get reaped. Otherwise, it just wouldn't work. So you let it be acquired for a zombie task. You let the timers get accumulated. Let the lock get released. And at this point, you can reap the task and free the timer. And then when it gets processed, a use after free happens, right? And so on the right, you can see the scheduler interrupt would have to happen, again, after exit notify, because that's when the task becomes a zombie. But yeah, that's just the gist of the bug, right? So I'm going to quickly, I know that was a lot of different concepts. I'm going to quickly just summarize the steps you would need to take before I get into the actual proof of concept construction, right? So lots of text, but basically, you want to create a task A, right? And this task creates a timer that is supposed to fire at some point in the future. Then you have another task B that p-traces task A to prevent it from dying, so it can become a zombie. And then you want to exit task A at just the right amount of, just the right point in time, so that A, that timer that you set up is ready to fire right when it's exiting, and B, an interrupt, so again, this on the right here, this interrupt needs to happen after the task becomes a zombie, right? And the timer needs to be ready to fire at this exact time. So this function on the left, which happens during the interrupt, can process this timer. So assuming you have all of that set up, task B now, and this is step 5, right? Assuming you have all of that set up, task B now waits for this window, this reap task and delete timers window. It waits for this, and as soon as it sees, like, okay, the timer is in a local variable now, so I can reap the task and delete it. So it does that, and as soon as that happens, obviously, if the timer is deleted and it gets processed, it's a use after free. And that's the whole idea behind this bug, right? So yeah, that's a lot. So I'm going to go into how this proof of concept is written, right? There's a few things or few problems to solve to get into how you can trigger this bug, right? The first problem, I'm going to drink some water real quick. So the first problem is that you need to be able to set up task A with a timer that expires at just the right time and get that interrupt to occur at just the right time. It's much harder than, I think this took me like 2 days to figure out just to do this part, right? So how can you do this, right? Now, the key point here is that this interrupt on the right, this can never fire too late, right? Because you have 3 potential scenarios here. First, the interrupt fires too early, before exit notify is called. If that ever happens, then the task is not a zombie, which means it cannot be reaped and the timer can't be deleted. So nothing goes wrong. You don't get a use after free, nothing happens. You can just keep retrying over and over again until it happens again, right? The second thing that can happen is it happens after exit notify, the right time, and assuming the timer is ready to fire, now you can delete this task, reap this task and delete the timer, get use after free. Now, if the task dies before this interrupt happens, that's it, right? When the task dies, it doesn't consume any more CPU time, so you can't get an interrupt to fire anyway. So that can never happen. So you can have this interrupt occur too early, but never too late. And yeah, so I don't know why this slide is here, but I think it's just explaining that you want this interrupt to happen at this point in time because you need to be able to reap the task, right? It has to be a zombie, right? So our goal is basically this. We want to set up a timer, and then we want to somehow control how much CPU time we waste or use up, such that when we exit this task in which we created the timer, we pray that an interrupt happens after it becomes a zombie task. We pray because we can't control when an interrupt happens, right? We don't know the state of the CPU at any given time. So it can happen at any time. We just hope and pray that it happens after the task becomes a zombie. So in order to do this, first we have to set up the timer. So setting up a timer sort of looks like this. You set up the SIG event structure, and you specify what you want to happen when the timer expires. In this case, we say we want to send a signal, and this signal we define as SIG user1. It's a user-defined signal. And then we create the timer using timer create, and we use a specific CPU clock. It's not important why we use this clock. This is the clock that's needed for this vulnerability. That's why we have to use it. And we use this event structure for this. And a quick note, timers are attached to their own processes. So you cannot share timers across processes, but you can share timers across threads. But threads and processes themselves are both tasks. So it might be a little bit confusing when I say tasks and then processes and threads. It's just the terminology that the kernel uses, right? So anyway, important thing, timers can be shared across threads, but not processes. Now, when we want to arm this timer, we do something like this. We have this iTimer spec structure, and we specify this nanosecond parameter. So in this case, I set it to 1 millisecond in nanoseconds, just a huge 10000 value. And you can ignore the for loop. That's for the actual exploit. I'll explain later. But at the end here, you can see I'm setting this to 1 millisecond, and we arm it using timer set time. And all this means is in 1 millisecond, fire this timer. So send whatever sig user 1, that signal that I just showed, send the signal to whatever process needs it, right? So as I mentioned, so our first step is done. We set up the timer. Now our second step is to waste enough CPU cycles to run down the timer. But how do you know how much CPU cycles to waste? And in this case, the way I did it is I picked the simplest system call that you can find on Linux, which is get PID. It just gets the process ID of the current process that's calling, making the system call. And I basically benchmark it, I think 10,000 times or something in this for loop at the beginning. And so basically, I just use RDTSC. So this doesn't work on Android because ARM64 doesn't have RDTSC. It's only on AMD64, but yeah, basic or x86, sorry. And yeah, so you just take the time at the beginning, make the system call, take the time at the end, do it 10,000 times, and average it out. Right? That's me just benchmarking the system call. Once I have this benchmark, I have the average time that the system call consumes. So this is task A. In the context of task A, it's just a thread. So this is a thread function. So all I'm doing after setting up the timer and whatnot, I have this for loop where it takes 1 millisecond in nanoseconds, divides it by the average CPU time consumed by get PID, and then I have this threshold variable, which is not important here for this context, but this syscall loops time or loop times variable, it's a dynamic variable, right? Because remember, our interrupt can fire at any time, but what we want is the timer to be ready when the interrupt fires, right? Now, if the timer never fires, then we know that the timer was armed. Sorry, if the timer never fires, then we know we didn't waste enough CPU time, right? Because if the timer's supposed to fire here, and we waste this much CPU time before exiting, then it will never fire because now it's just exiting. Now, if the timer fires too early, then we don't get a zombie task, right? Sorry, the interrupt won't happen at the right time. So basically, anyway, you have the timer firing too early or too late or right in the middle. Depending on what happens, I modify this variable in the exploit to either waste more CPU time or less CPU time to just get the exact time right. And after that, we just return. And when you just return from a thread function, this is what triggers do exit. This is what triggers the actual, make this task into a zombie and then cause an interrupt. So our first problem, the solution summarized is you just create the timer, and then you p-trace the task from a different task. You benchmark get PID, the system call, and then you want to dynamically figure out how much time you need to, CPU time you need to consume to get do exit to be triggered with the timer firing at the right time. And then if that all happens correctly, you just have to pray that this interrupt happens at the right time. That's all. And yeah, that's the first problem solved, right? Now, the second problem is after step 5. I mentioned, so if you read this, it just says task B now waits for task A to be in the interrupt, for the timer to be in the local variable, which is, I'll just go forward here, it's this part. So the timer needs to be accumulated into this local variable, and then task B needs to reap task A. But simply waiting is not a reliable way to figure out, oh, when do you need to reap this task? So we need to figure out a deterministic way to figure out when is this siglog being released? How can we do that? Because we don't really have any primitives here. We don't really have, from the user land, you can't figure out when a kernel mutex is being released, right? So you need to find a different way to figure this out. And so my solution was to use multiple timers. So in this case, when these timers are being accumulated, again, this is a simplified explanation, but it can accumulate up to 19 timers at once and handle all 19. So my idea was, instead of in the exploit, I use all 19 timers. I'll explain that in a bit. But let's say you use 2 timers, right? So you have one timer that's an oracle, and then one timer is the timer that you're going to free and have a use after free happen. So that's what this would look like. So sorry, before I get into that. So when a timer sends a signal, on Linux, you can create what's called a signal FD, a signal file descriptor. And if the signal arrives, this file descriptor gets a signal in it that you can read out of it, right? So that's basically all it is. And since it's a file descriptor, you can pull on it and you can wait on it. So a process can block on this file descriptor, signal arrives, the process wakes up, right? So the whole idea here is we use 2 timers, ignore the for loop, that's for the 19 timers I mentioned before, but in this case, let's just assume there's only 1 timer, right? We have this race event, right? This is for the oracle timer at the beginning, and it fires sig user 1. And the whole goal here is when this signal gets fired, we have task B, right? That's waiting for task A. All it does is it polls for the signal that this Oracle timer is supposed to send. And this is what the polling looks like. You create a poll FD structure. You pass it the signal FD of the signal that's being fired, in this case, sig user 1, which we specified right here, right, in this code. And then you poll for it, and this poll call right here will block and wait until that Oracle timer fires a signal. As soon as it fires a signal, we know we're in the race window, right? Because as soon as we're in this process timers part, right? And our Oracle timer is being handled before our UAF timer, the second one. So Oracle timer fires the signal. As soon as this happens, so the reaping happens in a different part of the exploit, so that's why you don't see it here. But you can see as soon as we get this signal, we delete the UAF timer. So this is now completely deterministic, right? The Oracle timer tells us, hey, I'm being processed right now, so you can delete the timer that comes after me and then get a use after free. So that's that problem solved, right? So quick summary again. We set up 18 stall timers. I'll explain why in a bit, but let's assume there's one Oracle timer now. So we poll for the signal from that first Oracle timer, first stall timer, and as soon as we get it, we just reap task A and then we free it. That's it. That's how we deterministically get the use after free, assuming we won the race condition at the beginning. So now a real quick note about exploitation that's going to show up in a bit is this is the function that frees the timer. And you can see at the bottom here, it uses RCU to free the timer structure. And RCU in this case just means that the timer isn't freed immediately. It's deferred for later, right? So you wouldn't get a use after free on the timer itself. But this second line, this timer sig Q variable, that variable is what contains all the details about what signal is to be sent, which process needs to get the signal, all those details. This structure is freed directly. This sig Q free function just frees it immediately, right? So that's actually where the use after free happens. And you can actually detect this use after free without address sanitizer or anything else, right? And the way this works is when the timer is processed, this send sig Q function is called, right? And this happens in the interrupt context. And you can see there's this bug on at the bottom. And it's basically, this Q is that sig Q, right? This Q variable is this timer sig Q. And it has a flags field. And it's basically checking for this pre-alloc flag. If it doesn't exist, it'll crash the kernel thread. And so this pre-alloc flag is set for sig Qs that are allocated, but it's not set for sig Qs that are freed, right? And remember, our goal is to free this timer before it gets processed, right? So if we free the timer, the sig Q is going to get freed as well. And so we're going to get here, and this flag is not going to be set. And so that's how initially, when I wrote the proof of concept, I saw this bug on get triggered, and I knew, OK, I hit the bug. So the proof of concept worked. So now we have two more things to cover before going to the exploit. So the third problem is in step 7 and 8, where, and I'm going to skip real quick forward. I'm going to just show you. It's right here when you reap the task and delete the timers. Now, if you just have two timers, one timer sends a signal, and then you reap the task and delete it, technically you don't have enough time. Okay, by default, it's like nanoseconds, right? It's gonna get the signal, and then it's gonna process the second timer immediately. It doesn't take that long to send a signal to another task. So you don't have enough time to reap the task that contains the timer and delete it. So that's what this step is. The problem is, isn't the race window a little bit too short? And it is, right? Now, the solution to this, I kind of stole from Jan Horn. I'm sure a lot of people might have probably read this blog post when it came out back in 2022. I'm not going to go into the details about the exact implementation, but basically the idea here is instead of using two timers, like I mentioned, now we have 19 timers, where the 19th timer is our use after free timer. That's the one we free to cause a UAF. But all of the other ones before that, so the first one is the Oracle timer. That's what we use to determine we're in the race window. But the first 18 timers altogether, we have a signal FD, right, for the signal that they send, sig user 1. And we duplicate the signal FD 100 times to create 100 different file descriptors. And this step 4 is from Jan Horn's blog post directly. You create 500 epoll instances, and these are, you can think of them as tasks that can watch these signal FDs, and they can react if a signal gets sent to them, right? So you set up 500 of these, and you have each of them poll on every single of these 100 file descriptors that we duplicated. And then when each of these timers fire, the first 18 ones, they will need to loop through and wake up 100 times 500 equals 50,000 different waiters 18 times. And waking up a task that's sleeping on a signal FD or any file descriptor is not a simple thing. It has to go through a whole bunch of different kernel components and then wake it up and then come back. And then it has to figure out, should this other task that I'm waking up, should it be context switched into now or should it be context switched into later? There's a whole bunch of logic, right? So basically, this is how this nanoseconds race window gets extended to about 30 milliseconds. And that's more than enough time for you to reap the task, delete whatever timers, and go to bed, do whatever you need to do. So you have a lot of time, basically. So that's how I extend the race window, and we get enough time to free the timer. The last problem is, how do we know when this scheduler interrupt right here, how do we know that that fired at the right time? Because remember, it can fire too early, or it can never fire when you're in do exit. And my solution to this is to abuse the use after free that we get, right? So I'm going to go to the next slide. And so this is the situation we have, right? We have 18 timers that I make it send sig user 1. And then we have the UAF timer, the 19 timer, which I also make it send a sig user 1 signal. Now, assume that we won the race. We were able to delete this UAF timer. My idea here was, as soon as it gets deleted, I immediately reallocate it, and I change the signal on this reallocated timer to sig user 2. And now, either we win the race and we have use after free, or we don't win the race and we don't have use after free. If we lost the race, then we don't have use after free. So this reallocated timer would be its own thing. This signal would not be in the same memory address as this one, right? The UAF timer. So in that case, we would see 1 plus 18, 19 sig user 1 signals. So if we ever, in the exploit, if it ever notices 19 sig user 1 signals come in, we lost the race, just try again. That's fine. But if we were able to free this UAF timer before it's processed and reallocate on top of it and change the signal because of the reallocation, then we would get 18 sig user 1 signals and a 1 sig user 2 signal that we technically never sent, because this new timer, we just allocated it. We never used it. So as soon as we get a sig user 2 signal, we know that we won the race. We know that the interrupt happened at the right time. The timer was set up and armed perfectly. So everything worked out. So that was the solution to this final problem, right? Now, after this, we need to figure out a way to get reliable use after free. Because remember, this use after free that we have here, first of all, it happens in an interrupt context, right? So this CPU interrupt can happen at any time. It's not reliable. And this sig queue structure that we have the use after free on, it's really simple. It doesn't do anything. All it does is it contains some information about the signal being sent, and that information can get used, but you don't get like a use after free write or anything. It's kind of useless. So we need to figure out a way to take the use after free out of this interrupt context and into a different normal execution context so we can trigger it at any time, whenever we want. So that's the goal, right? Turn this use after free into a better and more reliable UAF that we can trigger at any time. Now, remember that we have this reallocated sig queue, right? And remember that this flag is set for any sig queue that's allocated. So when we have reallocated over this sig queue, this flag is actually set again. So we don't hit this bug on at this time, right? So, but remember, we can know that we won the race because we get sig user 2 instead of 19 sig user 1s. So at this point, we've dodged the bug on, so the kernel doesn't crash. But now we need to figure out how can we, like I said, get a better UAF. And to figure this out took me 3 days of just trying a whole bunch of stuff. Like 8 hours a day, probably. I think I was on holiday from work, still at home, but just doing this. So now, to figure this out, like I said, okay, so let's talk about what caused me to figure this out, right? So I realized that in this situation, we have this setup. We had UAF timer, and it had a sig queue, and we freed it. And then we have reallocated timer, which has a sig queue, but they both point to the same memory address, right? So the idea here now is that we want to somehow have this sig queue be put in multiple tasks at the same time. And again, I'll get to why we need to do that, but basically that's the idea that took 3 days for me to come up with. And so the whole idea hinges on this check. Okay, this is in send sig queue, right? That function that is called in the interrupt context. So basically, this queue is the sig queue. Okay, this Q is this SIG Q. And the first check, and this is what made me question this is what made me figure it out. I asked myself, why is this check even here? So it basically is checking, is this signal already existing in some task's pending list? If it is, then that task can handle the signal, right? So basically it's checking, if it already exists somewhere, don't insert it somewhere else. Just increment this overrun variable that's here and just exit, just return, right? But if it doesn't exist on some list already, then you can, first of all, call signal notify, which is what we use to extend the race window. Remember, it's going to go through 50,000 different things and notify them and wake them up. But more importantly, it's going to add this SIG queue to a different task. That task's list is called pending here. And it's going to add it to that task's pending list. So that's the way, generally, how signals get passed between tasks. Each task has its own pending signals list. And a SIG queue variable is appended onto it. So the task can later see it and handle it. Okay. So now what does this list situation look like? It sort of looks like this. So let's say you have two tasks, and this SIG queue is on one task's pending list. So each of them has a next and a previous variable. These are linked lists. And so they both point to each other. Okay. This is the normal situation. Now, the question was, why is this check here? Why do we need to check to make sure it's empty? And the whole reason is because this SIG queue only has one set of next and previous variables. So if you were to insert it into two different lists, you get this situation where the SIG queue's next and previous variables can only point to one list or the other, not both, never both. But both of these tasks can have this SIG queue technically in their pending list. Now, the issue with having it set up like this is that if, for example, in this situation, task 2 was to go through its list, take the SIG queue out, and handle it, and it would free it at that point because the signal is handled, it gets freed, you end up in this situation where task 2's list now just points back to itself. This is the default state, by the way. It just means the list is empty. And the SIG queue that got handled now also points back to itself because it's done. It got handled, and it's now free. That's the important thing. But task 1's pointers still point to the SIG queue because those were never reset, right? And this is exactly how, in this situation, we get reliable UAF. You have a freed signal that's forever stuck on task 1's pending list, and you can take it out, free it whenever you want. You can do you can process it basically whenever you want. So, and obviously, the SIG queue cannot be removed from task 1's list ever because the pointer's all messed up, right? If you try to remove it, you get the same result like over and over again. So you can trigger this use after free anytime you want. So how do we do this, right? So this is the idea. We want to get to this state. So we have a freed signal on a task pending list. We can process it whenever we want. How do we get to this stage? Well, remember that send SIG queue function. It does basically this, right? It checks, is this signal already on some pending list? If it is, okay, don't append it, just don't do anything. But if it's not, then we have the second race window opening up, which I'll explain shortly. But you will notify and wake up all these waiters that are waiting, and then you will append it to whatever the target task is. You let it handle it. So, and in code, this is what it looks like, right? You have this empty list check. Right after the check finishes, you have a second race window. This race window can be extended using the same logic from before. And then the window closes as soon as this signal is appended to some task list. And so what can we do in this race window? Well, the idea is this, right? This check is happening for the UAF timer. And I'm going to skip forward real quick. This is the situation, right? We have UAF timer SIG queue and reality timer SIG queue both pointing at the same place. It's the same SIG queue. So the idea here is after this check has happened, the race window opens up, we use reallocated timer and insert this same signal, right? It's the same SIG queue. We insert it really quickly into some different tasks pending list, right? And it's allowed because they're two different timers, but they're pointing to the same signal. So you quickly insert it, and you have to do it in the race window because otherwise this check will cause the signal to not be inserted, right? So you have to do it in this tiny race window, and as soon as you achieve this, you end up in this exact situation. You have two different tasks with the same signal that can be processed. And real quick, just in code, with the reallocated timer, in order to insert the signal, all you have to do is you set the time to the past. In this case, it's 1 nanosecond after 1970, whenever Unix time started. And you use this timer absolute time flag when you set the timer. That's it, when you arm the timer. And it'll fire immediately and cue the signal to whatever task, right? So we have this situation. And right now, what we want, again, is for task 2 to process the signal so that it gets freed, and task 1 will have the signal now. So in order to do this, it's very easy. Remember that this signal is now sig user 2. We just have sig user 2's signal FD, that's right here, and we just read from it, which means just take the signal out, process it, and free it. So as soon as we do that, we end up in this situation. And from here, we get to final exploitation, right? So yeah, so now we have task 1 with the signal forever in it, and you have use after free whenever you want. So now I'm going to go into final exploitation, and this is the part. So this part is also pretty complicated, but I have 8 minutes left. And so I'm going to just quickly go through without getting into too much detail about exploitation. So the whole idea in this case was we have this freed SIG-Q, and now I used this thing called cross-caching, which basically the SIG-Q comes from a specific part of the kernel, a specific cache in the kernel. And if you want to reallocate another type of structure on top of it, it's not as trivial as free SIG-Q, allocate another structure, and then it goes on the same space. You need to do a whole bunch of SIG-Q allocations, free it in a specific way such that the page in memory where the SIG-Q is, it gets reallocated as a different type, right? So in this case, my whole idea was take the SIG-Q, use cross-caching to replace it with a pipe buffer. Now, pipe buffer pages you can just think of as a memory space where you can read from and write to it freely, any way you want, right? So that's what this diagram is supposed to, I guess, show. So you have the SIG-Q, you just scribble over it, and you override it with a pipe buffer page. And then inside the pipe buffer page, you still have the SIG-Q is still there, right? It's still in task 1's pending list. So it still has a next and previous pointer. So using this pipe buffer page, you can read those pointers out, right? And the reading sort of just looks like this. You just call the read system call on the pipe buffer's file descriptors, and you can read out of it. And this is output from the actual exploit. You can see it reallocates the UAF SIG-Q as a pipe buffer, and then you get a bunch of kernel pointers as leaks. And for the exploit itself, the only thing that was important is that we basically, when you have this situation, you send another real signal to task 1. So that's this SIG-Q's next pointer, right? It's a linked list, right? So this next pointer will get overridden with another signal, and you just leak this, right? And this signal is on a completely different page, completely different part of the kernel memory space. And so once you get this, now we have to look at, okay, we have a heap leak. We have a leak of a heap page. What can we do with this? So the only useful primitive that I could find was when you're freeing a SIG-Q, you have this line in the middle where it goes into the SIG-Q, goes to this user address, which again we can control because we have a pipe buffer on top of the SIG-Q. We can override any of these pointers. So we have this user variable, and then it goes and it decrements this SIG pending variable by 1. So if we just override this user variable with whatever kernel address, we can just decrement something, whatever value is there. So now the question is, what do we decrement? And yeah, so this is just an illustration to show that we can override these pointers with the pipe buffer. And it's not just the next and previous pointers. Like I said, there's a user pointer. There's a whole bunch of other data that you can override. So we have arbitrary decrement. What can we do with this? So my idea was we know this address, this valid SIG-Q allocation on a different page. We know its address, right? So my whole idea was we do cross-cache again, except this time not with the use after freed timer SIG-Q, with this other valid SIG-Q. We do cross-caching here, and we reallocate it as a struct cred. So a credential structure in the Linux kernel is basically just part of a task, and it has a whole bunch of different fields. But what we care about is this EUID field, which basically is just the effective user ID of the process. If this is 0, then the process is root, right? So my whole idea was, again, you have this other signal page that we know the address to on the heap. We cross-cache that and overwrite it with allocations of struct cred, and then we use this arbitrary decrement primitive right here to reduce this EUID all the way down to 0. And as soon as it's 0, we can spawn a shell, right? So basically, yeah, that's what this would look like. So you have this other SIG-Q, this address, you know what that is. And you could do cross-cache yet again. So this other SIG-Q, you override it with struct cred. And then there's going to be a lot of code coming up. But basically, this is what it looks like, right? In the first part, you have this pipe buffer page. where you have the UAF SIG right? So here is me setting up the list next pointer, the list previous pointer, so you don't get a crash when you free it. Because remember, this decrement primitive happens when you free the SIG. So yeah, I'm setting up those pointers. I set up the signal to be SIG-RT min +1. It's a real-time signal. Doesn't matter what the signal is, it's just a value. And then we set the user, so this is the user offset, we set that user pointer to point to our target the credential structure address, which we got from here, right? It's this page, somewhere in this page. We have a credential structure after the cross-cache. So I set it here, and then -8 because that's where the SIG pending variable offset is. And then we write it. So we use the pipe to override all these pointers. And then in this for loop, you can see it just goes and reads out of SIG-RT1, which is in this case, if I just go back real quick, it's basically reading this SIG from task 1 and then freeing it over and over again, right? Every time it frees it, we have this decrement. So we just free it, get UID amount of times, because whatever the UID is now, we just free it that many times, we decrement it that many times, it becomes 0. And yeah, after this, you can just find this process, spawn a shell, and that's it. So hopefully, I'm going to go into the demo now, but hopefully that wasn't a whole lot of information that confused everyone. But OK, so the demo is just going to be a GIF, so I can't pause it. But I have a screenshot afterwards with the relevant output. So basically, in the demo, I'm going to show there's a flag. You can't read it. And then I run the exploit, and you'll see a bunch of output, and then I cat the flag, right? So it's already running. I'm just waiting for it to reset the GIF. OK, whatever. You can see it. Oh, OK. It's OK. Yeah, there you go. So that's QEMU running. Show the flag, cat flag. Hope it's readable. Yep. OK, so yeah, permission denied. So now it's attempting to win the first race. Not enough time to read everything. I'm sorry, when it wins. So now you have a root shell, and the flag was just this, just some ASCII art. So, okay, thank you. So I'll just real quick, I have 2 minutes, I'll just talk through some of this output. It's just a screenshot here. Yeah, basically at the beginning, it's trying to win the race, right? It's just the very first race in that handle POSIX CPU timers function. After it does, we have a freed UAF SIG queue, UAF timer, whatever, and we know where it is. And then we cross-cache it with the pipe buffer page, and then we get these leaks. And the important leak, again, is this other SIG queue. The others are just a bonus. And then we cross-cache this other SIG queue yet again, and we override it with credential structures. And the way I did this was I forked 1,000 different processes, and then I just used those processes to spray a bunch of credential structures. And after we do all of that, we know the address of the page that has the credential structures. We just decrement a random one. It doesn't matter which one. We decrement one of their EUIDs to 0. And then we go through all 1,000 of these processes, and we just get all of them to call get EUID. And whichever one returns 0, that's it. We just tell it to spawn a shell, and then we have the shell at the end. And so, yeah, that's all. I have literally 30 seconds, so I'm not sure if there's enough time for questions. But yeah, that's the presentation. So.
Thank you. Great presentation.